Antonio Santo. I'm a predoctoral. My name is Antonio Santo. I'm a predoctoral researcher from Miguel Hernández University. I'm going to explain what my research is about. The title is Where Should I Walk? Computing the Traversability of the Environment. So, well, the question where should I walk for an AI, it's not a trivial problem. So autonomous navigation, which has been a subject of study for decades, right now can be addressed under a new paradigm, the supervised learning. So my research tries to model the world around the robot into traversable or non-traversable space using deep learning techniques. So for understand the traversability concept, we need first to define it. The problem of traversability is considered, traversability evaluation is considered as a semantic segmentation task. So given a representation of the world by a LiDAR sensor, we obtain a point cloud, and the point cloud can be defined as points, features, and labels. The points are the coordinates in the Cartesian space. The features are qualities that belong to the points, and finally, the labels are the traversability condition that can be 1 or 0. 1 if the point or the area is traversable, and 0 is the point is not traversable. Thus, the problem can be defined as a point-wise binary classification problem, although can be addressed under a regression problem. So, in terms of the approach we are working on, we have this robotic platform called Husky, which we added new sensors like the Auster LiDAR and the GPS. And for the data that we are using for training the deep learning techniques, we use very well-known semantic data sets in the artificial vision area, like Semantic Kitty and Realist 3D. Both of them we had to adapt to the traversability problem to become into only two classes, traversable or non-traversable. So, like I said before, we used point clouds as input data. So we start from the concept of convolution. However, when we try to define a space in 3 dimensions, the convolution that we can see in problems like images recognition or classification is not worth. So we use sparse convolution. That the sparse convolution focuses the convolutional window only in the space that there are points. So it's more efficient in terms of computation. This is the architecture that we are training from scratch with the data sets that I mentioned before. It's a sparse neural convolution network. Gives an output, a binary segmentation of the points into traversable or non-traversable. Here, we can see some results. On the left side, we can see the ground truth is a perfectly labeled point cloud. And on the right side, we can see an inference from the sparse convolutional neural network represented as a confusion matrix. So in green and blue, we can see the true values, true positives and true negatives, and in red and black we can see the false positives and the false negatives. So that's all for me. Thank you for listening to me, and see you around.
Hi everyone, I'm Paula Soriano and I'm a PhD student at Miguel Hernández University of Elche. My thesis is called Development of Cell-Tuning Brain-Machine Interfaces for Gait Control of Lower Limb Exoskeletons. So, can you imagine a future where people with motor disabilities is able to walk again? Well, my thesis basically is based on reading these patients' minds and try to make this possible. So basically, a brain-computer interface translates brain signals into commands to control exoskeletons, for example. When they are based on motor imagination, the subject has to imagine that they are moving their muscles. So this helps in the rehabilitation process because they get directly involved. The main problem when this paradigm is used for gait rehabilitation is that due to the region of the brain that generates these signals, they are weak and difficult to detect. So the accuracy of the system is not as high as we desire. Another component of my thesis is the error potential, which appears when something unexpected and wrong happens. For example, a person is walking with an exoskeleton and it abruptly stops. The main advantage of this potential is that it's stable over time. So the main goal of my thesis is to develop a BCI to control lower limb exoskeletons for gait rehabilitation. It will be based on the motor imagination paradigm to imagine a start and stop the gait, but it's not necessary that they maintain this imagination while walking. It will be asynchronous, and also to overcome the accuracy limitations, it will be self-tuning with error potential to correct the wrong commands. Finally, there will be a validation process with spinal cord injury patients towards its clinical implementation. So here there's a global view of how the system will be. First, it's divided into subsystems. The static one, where the subject is stopped and imagines about starting walking. And the second one, which is the motion, where the subject is walking and imagines about stopping the system. So in a nutshell, for instance, the static system, the subject is quiet, it's stand, and at some point decides that wants to walk. So the first classifier of motor imagination detects this, and a feedback warns the subject about start walking. This warn will produce an error potential if the subject actually didn't want to walk and stop the exoskeleton. Otherwise, the exoskeleton will start walking. So there are basically two classifiers, the motor imagination one and the error potential. In the motor imagination, the signals can change every day, because if the subject haven't sleep well or is feeling stressed. So it's a system that has to be retrained in every session. So to enhance the training, I am going to create a database with signals from different dates and subjects. And for the error potential classifier, as I said before, it's stable over time. So I can create a generic one for multiple patients. The main problem of this classifier is that error potential only appears when the error rate is lower than 30%. So the dataset will be really unbalanced, and it's such a problem in artificial intelligence. Here there's an example of one trial, the trials we are doing, and during these months, I've just been doing trials to collect data and create the data sets. And create the database for the motor imagination classifier. And there's still a challenging journey ahead, but I want to face it. So thank you so much.
Well, hello everyone, I'm Alex Martinez, and I'm going to be talking about my thesis with its main focus on predicting student performance, but I'm also working on some game AI, and I'm also kind of collaborating with an Horizon Europe project called eDiploma. So this is an outline of these topics, and the first of all, we all know what is classic learning. It's a teacher-centered approach. We are in a class, the teachers talk to us, and we just have to do what they say. And recent years have proved to us that this may not work pretty well, so we've centered our approaches in developing the e-learning, which solves most of the problems of classic learning. But even with this, there are still some disadvantages that we need to focus and to solve. In our first work, we wanted to try to solve one of these issues, which is that in these learning courses, there are a lot of students enrolled, and therefore the teacher cannot reach every student and needs some help. And also in these online courses, there's a higher dropout rate than in classical learning. So we propose a classifier that can be able to predict whether a student will pass or fail their course, as well as if they will drop out or will they receive a distinction. For doing this, we will use the interactions with the resources of the course. No demographical, no any other type of data. Just the interactions with the resources, predicting the results. But just predicting the results at the end of the course will be useless. We need to be able to predict it when the course starts. So our second work was to try to predict it at different stages of the course. We used 10% of the course, 20%, etc. With this, what we wanted to create is a kind of a tool that will indicate the teacher, this student has a problem, you need to focus on him and you need to help him. And that's the thing we are currently working on. This is a completed work. So the next step we are going to focus is on try to detect which resources are critical. For example, it's a normal thing that you just have tons and tons of resources, files, videos, forums, that you don't know which one you have to access and which one will be helpful for you. So the main idea of our current work is to try to detect these resources and determine if there is potential files are better, videos are better, etc. Besides this, I'm also working on trying to develop some AI algorithms that will resolve strategic games better than the current ones, based on the number of steps they are visiting, the time they are taking, etc. And finally, I am also collaborating in a project called eDiploma, which is an e-learning platform where they are going to be using virtual reality, augmented reality, and artificial intelligence to help the students to be able to complete the courses. Right now we are in the phase of co-design, so we will be developing a platform based on a Moodle course where we will implement a recommendation system that will be able to indicate the students where you have to focus and which resources they have to visit. This is the part I will be implementing of. And that's all.
Hi, I'm Micaela Martín from the Shanghai First University, and I'm doing my PhD funded by ValgrAI. I'm going to present my work called Selection of the Best Viewpoint for the Camera's Placement in Video Games. The thesis objective is to develop intelligent algorithms using information theory measures for video games. Information theory was successfully used in graphic and robotics area, but there is still room for research in video games. In the initial work, we try to develop an intelligent algorithm for the automatic placement of the cameras in Unity. Unity is a game engine, and the method is based in information theory meshes. We use mutual information. Mutual information is a relationship between two probability distributions. In this case, it measures the relationship between the camera and the areas in the scene. And we choose these measures because it's converged and can be calculated in real time. The heuristic idea consists in the following steps. Suppose that X is the camera position and we have a scene S. So centered in the camera, we cast random rays on the unit sphere, so we have something like that. And we select only those that fall within the FOSDEM. And we observe the intersection point y sub k, this, of the ray with the first object in the scene, and calculated the normal to the surface at this point, this. So the method is based in the calculation of the continuum mutual information field between the camera and its viewpoint of the scene. So using Monte Carlo integration, we have this equation where A sub t is the total area in the scene, y sub k belongs to the differential surface, theta sub y is the angle between the ray and the normal to do the surface, and theta sub x is the angle between the normal at P and the ray. And the Unity 3D application was promising and present higher values for the scene view, apparently better to the human age. And as future work, we are going to apply this method to dynamic systems of the scene. Okay, this is all. Thank you.
Okay, hello. My name is Antonio Ferrer Sanchez, and I'm currently studying my second year of PhD. And my research mainly focused on developing new tools and new methodologies in order to apply deep learning in the numerical simulation of physical systems and physical scenarios. So I will start by explaining a little bit how the pins works. Obviously, what is a pin, and we will see a case of use, and so we will end with some conclusions. Okay, what is a PIN? The term PIN stands basically for physics neural information, or physics informed neural networks. They're basically a neural arbitrary architecture that's informed with a physical background. We can say that's an inductive biases. We basically force the neural network to meet some physical restrictions, depending on the field we are working on. And a PIN, okay, it admits as input, a physical input, the independent variables, so, such as time or space, and we output some variables that are physical variables. For example, if we talk about fluids, we can get the pressure, the energy, the density of the fluid, the velocity, etc. And since it is a neural network, how do we do the optimization process? Okay, so basically, we start, that's a big equation there, but okay, just focus on the second one. We use a loss metric function that's composed basically by several terms. The first term, this first term has to be with the underlying subset of equations, the partial differential equations of the system. And each one of these terms is related basically to each one of the extra restrictions that we can put on the system, such as initial conditions, or in time, or boundary conditions, and so on. So, as a case of use, big equations, that's the set of equations of relativistic hydrodynamics. That's a direct, let's say, continuation of the ordinary or classical Euler equations in order to describe the evolution of fluids in the Minkowski spacetime, okay, and it can be generalized. Okay, so the main purpose of the PIN in this case is just to predict the density, the velocity, and the pressure of the system. We can specify another set of variables, and I want to point out that the main advantage in this case of using a PIN in front of using a numerical algorithm or resolution is that the PIN doesn't care about the physical variables that we in fact have in the end. So I will jump just directly to a case in particular that we have been developing a new methodology to solve problems that have discontinuities, such as, for example, supernova that have discontinuities in density, for example. So we have been developing a methodology that's an adaptation of the baseline model that basically adds a new term that annihilates the attention that the PINs, the neural network focuses or puts over a certain area in space. And basically, we annihilate the zones that are dominated by high or steep gradients, such as discontinuity. So in this case, we proved on our last a publication that's in the peer review process, that by applying this new methodology, we're able to describe the jumps or the discontinuities, in this case is the density of the fluid, and in comparison here, this is the prediction of the baseline model. So we are able to describe a little bit better, let's say, the discontinuities we have in the variables. This is for the final time. In this case, it's a supernova, I think. I don't remember well, but I think that's a good example to show. And in order to finish some conclusions on this, that's clear that deep learning is nowadays one of the biggest tools we have in several fields. And in particular in physics, we use in general numerical algorithms that are focused on basically resolving some certain of problems. So they are, let's say, problem-dependent algorithms. So by using deep learning, we're able to adapt our necessities by just informing the neural network with the physics that it has to meet, it has to fulfill. So there's still a lot of room for improvement, that's clear, but every little progress that we can do counts. So thanks for attending, and I hope that have been useful for you all. Thanks.
Hello, good morning. I'm Bassam Hanna. I'm an ITian with MBA Master. I'm working with Emilio Olivas and Antonio Serrano. I'm going to talk about the deep physical therapy. Right now, or our goal, we are working with the physical department in the University of Valencia. Our main object is to compare and to have a new algorithm to use it with the post-stimulation, to use it in the sport, and to use it for the health, to use it with the physical therapy department, for the physical therapy and all the patient, the physical therapy part. Our planning right now is to collect the sample in the university with all the patients that come for each doctor who's working with them now. And then we are going to implement the data that we already collected and verify it in the stimulation for different sensors. The third part, we are going to make our new algorithm. And fourth thing, we are going to make, using the already post-stimulation algorithm, we are going to make the new one, and we will try to make it and use it on the for an app. A part of develop the app, we are going to use it on the iOS on Android. Our challenge right now or in the future depends on how it's going to progress. We are going to use the increase the accuracy of both of single or multi persons for the post-stimulation system, and all of it is going to be something useful. Hope it's going to be something useful for the health and for all the patient in the physical therapy part. And that's it. Thank you.
Hi, my name is Pablo Meseguer, and I'm going to talk about my PhD thesis titled Deep Learning Analysis for Histopathology Images. This is the table of contents of the presentation, and first of all, I want to highlight that my research takes place in the CVB lab, also called the Computer Vision and Behavior Analysis Lab, that is located in the same building. The team mainly works on image and signal processing, specifically with artificial intelligence and deep learning models. Applications of this work have been done in the medical and the industrial applications. Specifically, my work has focused on the healthcare field and specifically in the analysis of histopathological images. Just as a brief explanation, histopathological analysis is crucial in terms of the diagnosis of many diseases like cancer. It consists on the extraction of samples from the body, and they follow the mentioned histologic technique, and afterwards they are analyzed by the pathologist under the microscope. In the last few years, digital pathology have evolved to allow the digitalization of these slides, permitting its visualization in computers and its introduction to computer vision systems. I want to share the application of my work in two areas. First, the ulcerative colitis, and afterwards we'll see the skin cancer. Ulcerative colitis is an inflammatory bowel disease, and histology remission, that means the absence of disease, of active inflammation in the histological level, is crucial to determine if the patient is going to improve or is going to get worse. Our work has gone around the PHRI, which is a novel index for scoring biopsies from patients with ulcerative colitis, and it consists on the observation of neutrophils in 4 regions of interest. Neutrophils are a very important cell marker in this disease, and they have to be present, or they can be present in the lamina propria, the surface epithelium, the critical epithelium, and the critical lumen. So to attach this problem, we have proposed an algorithm called location-constrained multiple instance learning. Multiple instance learning fits very well the nature of these images because wall slide images, that are the digitalized slides, are gigapixel, so they cannot pass directly to the classical computer methods. So the multiple instance learning, what first of all does is to divide the slides in many patches, so they can go through the network. To help the network recognize the neutrophiles, we add a term called location constraint that help recognize these cells and better predict the ulcerative colitis. Finally, I also want to talk about skin cancer and specifically the prediction of multiple subtypes of cutaneous spindle cell neoplasms. In this field, we are investigating to apply continual learning, which is an area of research that pretends the continual development of deep learning models trained with data that arrives sequentially. For example, this fits very well the medical field where maybe we have a model that predicts two diseases, for example, dermatofibroma and dermatofibrosarcoma, and afterwards two new diseases are encountered. So if they are all related, we should retrain the model to also predict the new classes, the new diseases, but the knowledge of the deep learning model about the previous classes has to be retained. So we are investigating different approaches on multiple instance learning for continual or incremental learning. And that's all. Thank you for your attention.
Buenas, me llamo Sandra García Ponsoda y voy a presentaros el trabajo que estoy haciendo durante mi tesis. En primer lugar, voy a poneros en contexto sobre el proyecto en el que estoy trabajando. Luego voy a contaros qué he hecho durante este curso, qué estoy haciendo y qué voy a hacer. En primer lugar, nuestro proyecto se basa en el diagnóstico del TDAH. El TDAH es el trastorno por déficit de atención e hiperactividad. Estoy segura de que la mayoría de los que estáis aquí conocéis a alguien o tenéis algún familiar que padece TDAH. Entonces, la prevalencia de este trastorno no es nada desdeñable. Es un trastorno que aparece en la infancia, afecta al neurodesarrollo y es crónico. Sus principales síntomas son la inatención, la impulsividad o la hiperactividad. De acuerdo con la Asociación Americana de Psicología, el TDAH todavía no tiene una causa específica, es decir, no sabemos qué lo origina. Para ello, los médicos y los psicólogos que tratan de diagnosticarlo se basan en el Manual de Trastornos Mentales, la quinta edición, el DSM-5. Este manual contiene unas pautas de comportamiento en el que se basan los médicos y los psicólogos. Un estudio muy curioso que me pareció muy representativo es que si al diagnosticar el TDAH unimos las pautas del DSM-5 con métodos más sofisticados, el ratio de prevalencia del TDAH puede disminuir hasta en 10 puntos. Es decir, la variabilidad que existe en el diagnóstico depende mucho de cómo se diagnostique. Esto es lo que queremos evitar desde el proyecto ValgrAI. Queremos crear un diagnóstico del TDAH más objetivo y que sea más preciso. Para ello nosotros utilizamos electroencefalogramas, que son los cascos estos que vemos en la imagen, que graban la la actividad cerebral mientras que el paciente está realizando algún tipo de tarea. Durante este curso lo que hemos estado haciendo ha sido un tipo de review, Systematic Mapping Study, en el que hemos cogido unos 900 papers, más de 900. Y estos papers tenían en común que diagnosticaban una enfermedad mental y lo hacían mediante señales de ejes. De estos papers hemos cogido las transformaciones que se realizaban, las características que se extraían de la señal transformada y los algoritmos de selección de características. Esto nos ha permitido tener una visión global y generalizada de cómo se realiza el proceso desde que se recogen los datos hasta que se clasifican. Algunos resultados son estos. Las transformaciones más comunes fueron Wavelet Transform, Mode Decomposition y Fourier Transform. Y las características más utilizadas en estos estudios fueron parámetros estadísticos, características que se basaban en el dominio de la frecuencia y la entropía. Actualmente, nosotros hemos creado un modelo de Deep Learning que está basado en redes convolucionales separables 1D. Como ha explicado el primer compañero, en mi caso es 1D. Actualmente yo me estoy dedicando a la parte de la regularización. Para el que no lo sepa, las técnicas de regularización son todas aquellas modificaciones que se le realizan a los algoritmos de aprendizaje que tratan de disminuir el error de generalización, pero no el error de entrenamiento. Mi objetivo actualmente es encontrar un método de regularización que funcione correctamente con las redes que se basan en convoluciones separables 1D y con datos ejes. Finalmente, como estamos tratando con datos médicos, algo crucial es que necesitamos dar una explicación junto con la predicción que nos da el modelo, para poder explicarle de dónde viene esta predicción a los médicos o psicólogos que utilicen nuestro sistema de ayuda al diagnóstico. De esta forma queremos darle explicabilidad relacionada con la extracción de características que hemos mencionado anteriormente. Así los médicos y psicólogos pueden tener un mejor entendimiento de por dónde pueden ir las causas subyacentes del TDAH. La pequeña bibliografía y muchas gracias.
Hello everyone, my name is Beatriz. I am from Universidad Politécnica de Valencia. My advisor is Oscar Pastor. I am supported by ValgrAI in this research. My research is related with ontologies, ontology networks, for providing semantics to EI. In this scenario, we have a lot of applications for ontologies in the market. We have using ontologies for providing semantics for heterogeneous scenarios like data lakes, Internet of Things, many other stuff. The data are very heterogeneous. We have a lot of volume. So we have a very important scenario for modeling here. Well, in this scenario, we have two different perspectives in the stakeholders. We have the ontology engineering's perspective, which is provided the best model we can provide for the domain. And the domain specialists want effective results. they want to produce practical results. There is some kind of different point of view in this respect. This results some kinds of disagreement problems. We have, in the ontology engineering perspective, we have very well-founded models, ontologies in these cases. We have a lot of very good information, but we haven't data. And in the perspective of the domain specialists in the market, in the industry in special, they have a lot of data, but they don't have good models. The models lack from foundational basis, and this is some kind of problem we are facing. So in order to provide the necessary agreement for those stakeholders, we propose homogeneous scenario for ontological analysis and data evaluation. So we made these two important research questions related to the metadata. So what kind of meta characteristics ontologists must have to provide this kind of agreement, and how to provide management about these meta characteristics. So we proposed a framework. The framework is supported by very important, well-known best practice. One of those for data is the FAIR principles: findability, accessibility, interoperability, and reusability. So we use these principles to create a well-founded ontology. We call it O for OA, which for ontology for ontological analysis. This ontology classifies and characterizes the data in face of the different perspectives we are facing in. We face on the meta characteristics for the ontologies, and we face up the meta characteristics of the domain. In this scenario, we implemented this ontology using microservices. So we have an implementation, an API that manipulates the data we have in our research. And we have a set of guidelines based on that ontology, which provides some steps in the framework that is the basis of the framework. And at the end, we are creating an application, a web application, to assess and manipulate the data we have in the ontology implemented. Well, we are able to have some results. In this scenario, we have a company providing the data for us. We have data about cybersecurity. So we load this data in our environment, in our tool. We have some good results. We are present in some conferences. And the framework can provide this kind of homogeneous scenario. The framework has this cloud of concepts that provide support for EI in these scenarios, okay? Thank you.
Hi, my name is Behzad, and I'm a PhD student at UPV, and these gentlemen are my supervisors. I'm going to talk about data contamination. So let's first talk about AI evaluation. AI evaluation is a process that we measure the performance, the capability, and the limitations of AI systems. We usually take advantage of benchmark data sets in order to be able to compare the results and algorithm of different models and different research groups. So what makes the benchmark data set a good one? A good benchmark is the one that when you measure the model on this benchmark, it can map the result on the original data set, original distribution. And it also should be large enough, and it should not contain any ambiguous or mislabeled data, and it shouldn't contain any biases. So the problem currently with the benchmark is that they have a short lifespan. So previously it took several years, like 15 years in the case of MNIST data set, in order to AI models to get superhuman performances. But this is not the case now. The AI systems are getting very powerful. So when a new data set is introduced, the AI system gets superhuman performance very quickly. So like what teachers might do when they have very smart students is that they usually ask harder questions. So this is what's happening in AI also. We actually add more difficult instances in the data sets, or we alternatively, we remove the very easy instances, or we do both of them simultaneously in order to make our data set more difficult. But is this good? It turns out that it's not good for several reasons. The most important point is that this new data set is not usually representative of the original distribution. It contains biases, and the models are less reliable. So in our study, we propose a characteristic curve that is, can show the behavior of adversarial benchmarks more clearly. And what can be seen is that how these adversarial models behave in different difficulty bins. What we can see that in red, we see that the curve shows that these adversarial benchmarks lose their ability and their capability usually for the very easy instances, which is not really wanted, but they get more powerful for the very hard ones. What is clear is that in order to compare models, we should assess these adversarial models on the original distribution. So this system characteristic curves helps us do this assessments. And here we created different kinds of different adversarial benchmarks using different scenarios, and we can see that the pattern is always the same. So the adversarial benchmarks make the models weaker for the very easy instances and stronger for the very hard ones. So another source of contamination that we are studying is that the AI-generated content. So we know that so far the AI models are trained on human data, but this will not be the case in the following years because models like GPT-4 and Jolly can produce so good outputs that people put them on the internet deliberately or trying to fool people because they don't say that these are generated by AI. So why this is bad? Because these models usually contain inaccuracies, hallucination, and biases. And this might cause that the models that train on these data lose their performance. And also, they are less diverse than the human-generated data, and this can be also a source of contamination. Thank you.
Hola, buenas tardes. Bueno, me llamo Cristian Pérez y os voy a explicar un poco sobre lo que trabajo. Yo trabajo sobre Component Analysis for Reinforcement Learning en la parte de sistemas de manufactura eficiente energéticamente, ¿vale? Esto es un poco el índice que voy a tratar. ¿Qué es un sistema de manufactura? Un sistema de manufactura no es más que todos los trabajos que podéis pensar en la industria se pueden reducir a máquinas y trabajadores, por así decirlo, ¿no? Desde trenes hasta trabajadores de una empresa o cualquier cosa que se os pueda ocurrir. Entonces, nosotros generalizamos esto. ¿Qué puede tener uno de los trabajos? En general, los trabajos se pueden tener tiempo de procesamiento, el tiempo que se tarda en realizar un trabajo, el tiempo que hay entre la modificación de las máquinas entre un trabajo y otro, la fecha de inicio, la fecha de final del trabajo y, en este caso, nosotros trabajamos con energía, ¿vale? Para ser un poquito eficientes. ¿Para qué hacemos todo esto? Buscamos sacar un scheduling, una planificación completamente eficiente que sea eco-friendly, ¿no? Por así decirlo. ¿Cómo lo hacemos? Pues optimizamos las tres funciones que veis a la derecha, que son make span, setup time y energy consumption. Cada una está normalizada a los valores más máximos que puede tener en ese caso, en esa instancia en concreto, en ese problema, y la mínima, que suele ser 0, un valor muy bajito, ¿de acuerdo? Esta es la función que nosotros utilizamos, que es la minimización. A partir de esto, nosotros creamos, en lo que estoy trabajando ahora, es un sistema experto en el que, con muchos datos, lo que hagamos sea entrenar un conjunto, que entrenemos un sistema experto para que pueda solucionar eficientemente. Ahora veremos cómo lo hacemos. Para ello, el sistema experto recibe un dataset, que es un conjunto de instancias que tienen un montón de trabajos, un montón de máquinas y muchísimas restricciones, y le hacemos un component análisis. El component análisis se basa en 7 características que hemos estudiado de todas las instancias, que son el máximo make span, el tiempo máximo que se puede tardar en realizar todos los trabajos, la máxima energía que podemos gastar realizando esos trabajos, el time windows, que el time windows es la cantidad de veces que puedo realizar un trabajo dentro de una fecha de lanzamiento y una fecha final, la saturación de las máquinas o cualquier tipo de máquina que podamos utilizar, la saturación de los trabajos, es decir, cuántas veces un trabajo puede aparecer en un conjunto de máquinas, y el setup time, que es la cantidad de veces en la peor secuencia de máquinas trabajo que tengamos, las modificaciones que hay que hacer a las máquinas para que puedan realizar diferentes trabajos. Finalmente, el overlap es la cantidad de trabajos que se pueden solapar unos con otros, ¿vale? Que también es un factor bastante importante dentro de la optimización de los sistemas de manufactura. Con todo esto, lo que nosotros hacemos es una clusterización aquí está demostrada con 3 niveles, ¿vale? Son las 7 características, pero para poder agrupar realmente los trabajos en grupos por dificultad, ¿vale? A partir de eso, nosotros lo entregamos al sistema experto, que está basado en un sistema de reinforcement learning, de Q-learning en este caso. Sacamos los roadmaps que nos sirven para configurar eficientemente cualquier algoritmo que queramos utilizar para solventar nuestro problema. En este caso, nosotros estamos trabajando actualmente con el crossover y la mutation de los algoritmos genéticos y hemos decidido utilizar un algoritmo NSGA2. En futuro, nosotros lo que utilizaremos será diferentes tipos de algoritmos para poder decirte qué algoritmo es más eficiente en tiempo y en consumo de energía. Para ello, finalmente, obtenemos todas las soluciones y ya la empresa o la persona que esté utilizando el sistema de manufactura elegirá la solución del sistema experto. Muchas gracias.